Hi everyone and welcome to another video lesson, and this video lesson is brought to you by LifeWorks Math Online Tutorials featuring math vlogs from your tutor Man. You might be wondering and have the following inquiries like how to visually prove the definitions of the four important points of concurrency and four important lines in a triangle. Second question, what is an Euler line? How can we prove the Euler line's property where the centroid divides the interval joining the circumcenter and the orthocenter in the ratio of 2:1? Lastly, you might be wondering and ask, are there astronomical events that utilizes the 2:1 ratio of the Euler line in order to describe the positioning of any astronomical alignments? If yes, and you're interested in knowing more about the Euler line, its elements, and its proof, then join me as we appreciate and find joy in describing these great ancient mathematical concepts. In this video lesson, we'll be supporting Grade 10 Math. Our aim is to facilitate learning for the following competencies and standards: formulating and solving problems involving geometric figures on the rectangular coordinate plane with perseverance and accuracy. And for the learning competency, applies the distance formula to prove some geometric properties. You may perform the following performance tasks. Create a video illustrating the definitions and proofs of the four important points of concurrency of four significant lines in a triangle, or discuss the concepts and proving steps with your peers and a family member. After doing so, you may compose a reflective essay that emphasizes the practical implementation of mathematical and presentation skills in your everyday responsibilities and overall well-being. Start by constructing and proving the definition of the incenter. So let's create an acute triangle. ABC. Draw the angle bisectors and mark its point of concurrency as the incenter. So we are going to call the functionality angle bisector. So this one, click on angle bisectors and then choose 3 points. So for angle BAC, and then for angle BCA, and for angle ABC. And then we are going to mark its point of concurrency D. Point D is the incenter of the triangle ABC. Now for the proof of the incenter. So first we're going to draw lines that passes through the encircled D and that are perpendicular to each side of the triangle. So let's start with the side BC. So we're going to call the functionality perpendicular line and then click on side BC and then stop here at the incenter. So do the same for side AB and side AC. Now we're going to color the angle bisectors blue by using the algebra tool. So all we need to do is to find the components angle bisectors. So in this case, we have the components F, G, and H. And then right click on the 3 dots, click on settings, then click on the tab color and then choose blue. And then click on the style tab in order to increase the line thickness. Do the same for the other angle bisectors. Then you may label each one as an angle bisector, just like this. Now we're ready for the proof steps. So for the first step, we're going to color the 3 pairs of congruent. Now we're ready for the proof steps. So for the first step, we're going to color the 3 pairs of congruent triangles being produced. So using the polygon functionality here, then just select the 4 vertices of the quadrilateral. So we have A, G, D, and E. And then we're going to color this one lemon. And for our second pair, we're going to have a purple pair. So polygon, and then the quadrilateral, we have G, B, F, D. Okay, so this quadrilateral has a pair of congruent triangles. So we are going to color this one purple. And finally, we're going to have our orange pair. So just call the functionality polygon and then click on the vertices D, F, C, E. So this quadrilateral has a pair of congruent triangles. So this will be orange. These three pairs of congruent triangles have the following congruent parts. The first pair of congruent corresponding parts, we have the angle bisector as the common side. So the angle bisector BD is a common side. The angle bisector BC is a common side for the orange pair. And the angle bisector AD is a common side for the lemon pair. And we also have congruent vertex angles produced by the angle bisector. Here's an important note. The angle bisector divides a vertex angle into two equal parts. So for example, the vertex angle B, and we have the angle bisector BD. So the angle bisector BD divided vertex angle B into two equal parts, into two equal angles, GBD and angle FBD. And finally, we're going to have right angles formed by having a side perpendicular to the line segment connecting the incenter to the Z side of the triangle. The point of intersection is at the point of contact of the tangent line of the incircle. So let's create the incircle. So just click on the circle with center functionality, then choose the incenter and then stop here at either E, F, or G. Now I will present a sample proof of triangle congruence using these three pairs of congruent parts. Please repeat the same process for the other two pairs of congruent triangles. So let's prove triangle congruence for the purple pair. Alright, so for the purple pair here, this one. Congruent pair number 1. Side BD is congruent to side BD. So we have congruent sides, and the reason is reflexive property. So side BD is equal to side BD. It's equal to itself. Next, congruent pair number 2. Angle GBD is congruent to angle FBD. Congruent angles. Reason, the angle bisector BE divides the vertex angle into two equal parts. So we have the angle bisector BE or BD. So it divides vertex angle into two equal parts. So we can say then that angle GBD is equal to angle FBD. Next, congruent pair number 3. Angle BFD is congruent to angle BGD. We have congruent angles. The reason, side FD is perpendicular to side BF by construction. So let me show you. So we have side FD is perpendicular with side BF. Hence, triangle GBD is congruent with triangle FBD. And the reason is the side angle postulate. Therefore, we can conclude that side GD is equal to side DF. And the reason is CPCTC. Corresponding parts of congruent triangles are congruent. Furthermore, after showing congruence for the purple pair, lemon pair, and orange pair of triangles, we can state the important equality that side GD is equal to side DF, and side GD and side DF is also equal to side DE. The objective of this part of the proof is to logically show that after the angle bisectors were constructed and formed the incenter D, and after connecting such point of concurrency D to the sides of the triangle at the shortest distance, it formed line segments perpendicular to the said sides. Such perpendicular lines from the point of concurrency are equal. This can also be further illustrated by drawing the incircle. Again, we just have to show that line GD or side GD is equal to side DF and is equal to side DE. Lines GD, DF, and DE are the radii of the incircle. So here's our first figure. The incenter D produces equal line segments GD, DF, and DE that are perpendicular to the sides of the triangles at the points of contact between the incircle and the sides, where the sides serve as tangents to the incircle. Step number 3. Prove and demonstrate the congruence of the same pairs of triangles by proving that the pair of corresponding vertex angles are congruent. This pair of corresponding vertex angles is the pair of corresponding parts with missing or unknown congruence. So let's prove now triangle congruence for the purple pair. So congruent pair number 1, again we have side BD is congruent with side BD. Okay, reflexive property. Then congruent pair number 2, side GF is equal to side DF, right? Because side GD and side DF are radii of the incircle as proven in step number 2. Then finally, congruent pair number 3, side GB is equal to side FB. Alright, so we have congruent sides. And we're gonna make use of the Pythagorean theorem for our reason. So the Pythagorean theorem formula, c squared is equal to a squared plus b squared, is the distance formula for lines of right triangles. So we're going to have some algebraic manipulation here. Right, so again, side GB is missing, it's not given, and yet side BD is given and side GD is given. So we're going to square side BD, we're going to square side GD, get the sum of the two squares, and then get the square root. So we have this equation. Side GB is equal to square root of the square of side DB plus the square of side GD. Also, side BF or side FB is missing, yet side DF is given, and then side BD is given. So we're going to square FD, square BD, get a sum, and get a square root. So we have the second equation here. FB is equal to the square root of the square of side BD plus the square of side DF. And now we all know that side GD is equal to side DF as stated or proven here at section B. So we can do substitution now. We're going to replace side DF with side GD. So we can say that side FB is equal to square root of the square of side BD plus the square of side GD. Now, have a look at equation 1 and equation 3, or the first line and the third line here. Okay, so we have the same right side. So we can therefore say that side JB is equal to this expression, and this expression is also equal to FB. Okay, because at the first line and the third line, we have the same right side. So, considering transitive property of equality, then we can say that side JB is equal to side FB. Okay. Now we have proven congruency to 3 pairs of corresponding sides. So we can then say that triangle GBD is indeed equal to triangle FBD, and the reason is, of course, the side postulate. And since these two triangles are congruent, then all of the corresponding parts are also congruent. Therefore, we can say that angle GBD is also equal to angle FBD. So these are the two angles at the vertex. Hence, we have proven and shown that the incenter produces equal line segments that are perpendicular to the sides of the triangle at the points of contact between the incircle and the sides, where the sides of the triangle serves as the tangents of the incircle. Such equal line segments produces two congruent triangles with a common side, which is the angle bisector. And we have proven that indeed that angle bisector really bisects the vertex angle of the triangle into two equal parts. Here's now our conclusion. The point of concurrency of angle bisectors is the incenter. From the incenter, equal short distances extend to the sides of the triangles, forming the radii of the incircle. And the incenter is the point of concurrency as it connects to the vertices and bisects the vertex angles into two equal parts, constructing angle bisectors.